Hello and welcome to this LIGO-India podcast on gravitational waves. Today we have with us our guest, Professor Tarun Souradeep, Chair of the Physics Department at IISER Pune, that is the Indian Institute of Science, Education and Research. Professor Souradeep has worked in cosmology and gravitational wave science. Specifically, his work ranges from cosmic microwave background theory and observations to primordial perturbations and fluctuations in the early universe. He has also worked on gravitational wave backgrounds and contributed extensively to many science collaborations. Among other roles, Professor Souradeep is a member secretary of the LIGO-India Scientific Management Board, a council member of the LIGO collaboration, and a spokesperson for both LIGO-India and the Indigo Consortium, of which he is also a founding member. Professor, is there anything more you'd like to say to introduce yourself?
No, I just should say that, I have a career in starting in cosmology. And, so LIGO India is something that came, sort of about a decade or 12 years back. And, that's kind of a passion to get, frontier experimental activity in India. And that's my, key hope that LIGO India will bring that to India.
All right. So, to begin with, let's talk about your childhood and your early education and how you developed an interest in astrophysics. So, why did you choose physics? How come? What was it that led you into this field?
Yeah, so the story of going into physics is probably a lot to do with where I was brought up. So I was brought up in a locality in Delhi, very close to the National Physical Laboratory and Indian Agricultural Research Institute. So that's so later I realized many of us in my generation have actually opted for physics, and so it's not so surprising that I was interested in physics. However, as you know, I actually did an undergraduate in engineering. So it wasn't that I was completely sold on physics, but after a stint at the design, this thing of automobile design, I kind of realized that physics was my first calling. Astrophysics, I shouldn't, I should be very clear. And if you're brought up in Delhi, you don't get that clear sky. So I wasn't, heavily into astronomy, which is typically what attracts people. No, I was at the same level as any youngster would be, but nothing special. Uh, I think my journey into astrophysics is largely through the general theory of relativity. So amongst the courses in physics that I had taken, so I had to audit a lot of and credit a lot of courses from physics department. I've done a course on general theory of relativity, and a part of that course was taught by Professor Vishweshwara, very famous
CV Vishweshwara.
relativist, C.V. Vishweshwara. And to be honest, I didn't quite catch everything that he taught us, but he taught us. I have used his notes later to teach others, but at that time I didn't understand much, but I was really fascinated by the subject. So I think the journey, to be honest, is because I wanted to work on gravitation, and then cosmology is obvious. The happening place of gravitation. At least when I started, that was the most happening area. So that's my journey into astrophysics. So I am actually not very tied to a particular area of physics. I enjoy physics very broadly. I also enjoy engineering very broadly. So I I actually feel that young people should keep that openness. It helps.
Yeah, certainly. So this podcast is kind of focused on gravitational wave science. So we want to talk about, could you give us like a very general overview of what GW science is? Because for most people, it's almost like a very esoteric subject, like almost like Greek or Roman. So
Right.
Could you get into this?
No, it is as you would have heard many places. So the idea is we have electromagnetism, a well-known interaction, right? So we are quite used to the world of electromagnetism, which are excitations of the electromagnetic field, so electric. And we describe it with electric and magnetic field vectors. So just we imagine there are these vectors and things. But essentially, there's a field. Similarly, there's a gravitational field. We knew it from Newton's days that there is a gravitational potential. And what Einstein's theory does is, brings more richness to that structure, in the sense that we understand just not that the field has much more than just the gravitational potential. So there's one way of thinking about it is it's another field like electromagnetic field. But there's a neater way of wrapping it all up as the geometry of space-time. Okay, and so if you imagine we are all in a dynamic arena where the geometry is determined by the masses, then you can immediately ask the question, what happens if the masses move fast? And we know from other physics, even fluids and things, if you move a stick in a water, you generate ripples, right? Or if you move a charge in the electromagnetic field, it creates electromagnetic radiation, right? So similarly, moving masses create gravitational waves. This is something that was very quickly realized by Einstein, within a year of his general theory of relativity. And I think I should emphasize why I think gravitational waves is a big deal, is because that's the conceptually different observable from Newton's theory. Newton's theory cannot accommodate gravitational waves. Okay, I mean, besides the fact of speed of light and all that, which is what is told, you should realize that it has space for only a gravitational potential, right? So it doesn't have this richness that can give rise to these transverse waves. And so those are gravitational waves. And I would like people to think, and maybe in a century, people will just like we are used to electromagnetic radiation. And of course, we see some of that, so that helps. But there is a lot of things we are very used to, which come from electromagnetic radiation we cannot see. When someone measures the temperature of your body, you don't see those electromagnetic radiation, but they are electromagnetic radiation. Similarly, we will learn to understand that what mediates gravitational processes is gravitational waves, right? So although Earth is say, tied to Sun gravitationally, if magically Sun was to disappear, Earth will get to know of it only 8 minutes later, because everything is mediated through gravitational waves. And it is still, I mean, gravitational waves in terms of a field is a very nonlinear thing, but people have been thinking about it. In fact, in your institute, Kip Thorne keeps both the ways open, in terms of looking at it like a nonlinear interacting field, as well as this nice way of looking at it like space-time curvature and ripples on space-time curvature.
Yeah, I certainly think that it's a very good vision to try and demystify this whole gravitational wave science. So someday it's just as normal as the electromagnetism that we are all used to.
Yeah, I completely believe so. It is it's going to become a part of our lives now. Now people are not dazzled by thoughts of time being slow at some place, and these were concepts which were very difficult to accept a little over a century back.
Yeah. So to begin with, I mean, it would be most prudent to talk about how research in this domain could affect our daily lives. Why does studying gravitation, history of the universe, cosmology in general, why does it matter?
Yeah. So there are different ways to look at it. One is, gravitation. Of course, the fact that we have Einstein's theory is actually what allows you to use your GPS reliably, right? If you don't have the corrections to Newton's theory built into the GPS, you will get things totally wrong. Even though the correction for Earth is at the level of 1 part in 10 to the 9, right? But you are also trying to triangulate at a very high precision, right? So of meters. So that's clearly something that you're carrying in your pocket, which is affected by the whole understanding of gravitation. And of course, when you have a theory, you have perturbations on it, so you have a deeper understanding of it. So you should realize that gravitation, there are two aspects to really focus on. One is gravitational waves, whether they will be useful just like light, which already is very clear from the LIGO observations. We are understanding a lot more about astrophysics in the universe, astrophysical processes, because of the gravitational waves signals that we are getting and are able to measure them. We have been getting them all the time. But there's another aspect which is more conceptual. There's you everyone would have heard of the fact that we are still awaiting a theory of quantum gravity. Okay,
Yeah.
and you quantize a system which has radiative degrees of freedom, which has radiation in it, right? And that the fact that you have seen classical gravitational waves is the first observational step to show that there are these radiative degrees of freedom, okay, in gravitation. And what are they? And then, of course, I'm not saying this resolves quantum gravity, but this goes a long way towards it. In the context of cosmology, of course, the whole study of cosmology is largely, answering the question. I think humanity, being conscious beings, have been
Philosophically, yeah.
asking this question, right?
Yeah.
Who are we? Uh, Cosmology, to my mind, answers the question, where are we? What are we placed in? Where do we live? And that has revised our philosophy in terms of how we consider ourselves. Like, we know now we are like a tiny speck of dust, you know, completely insignificant
Yeah.
planet on an insignificant star in one of the billions of galaxies. So that perspective is very important. Okay, so it enriches people, it enriches human thinking. Okay, but also if you look at practically, why do we pursue such things like cosmic microwave background radiation? So one thing is, we are understanding the universe when it was just minuscule time away from what we think would have been a starting, or part I don't want to get delve into. But we know almost the entire history of the universe, right? And we know it fairly reliably now, and that has been possible because of this quest for measuring these things more and more accurately.
Right.
And on a practical thing, the kind of detectors you carry in your mobile phone, which receives the signals, those were essentially in the lab initially as detectors for such astronomical observations, right? So I believe things that are going into 5G were in the labs at Caltech. I know people who worked on it around the turn of the century. So you can see that it's not immediate, but over a few decades, every quest leads to things that are touching your day-to-day life.
Yeah. So you've kind of laid out the whole sample space of how to look at why this kind of stuff matters.
Yeah.
Um, so you briefly alluded to technological what could be considered as technological innovations that could be related to GW science. So one thing is
Mm.
GPS that was more generally allowed through Einstein's theory.
Yeah.
But do you have any kind of vision? So you mentioned that this is like cosmology is a philosophical thing and it can help us understand a lot for fundamental science. But do you have any kind of vision for how it could someday be used in daily technology, at a larger level? Now, of course, one can only speculate, but do you have any kind
Yeah,
of
for
vision?
gravitational waves, it's very clear. I mean, you already must be reading about, how gravitational wave observatories are using the quantum aspects, right? And, understanding and harnessing quantum phenomena for day-to-day life is becoming one of the most promising fields. And gravitational wave observatory is actually the mirror, if referring to a very recent work done at MIT, uh, which is keeping the mirrors, using the mirrors as quantum particles, right? You're using 40 kg mirrors to study their quantum behavior. And that is allowed because you had a quest that allowed you to control 40-kilogram mirrors to that kind of accuracy.
Yeah.
Okay, and the quest was gravitational waves, but what it is feeding into are very interesting things in quantum phenomena. Many of the techniques used to do this are now standard lab processes,
Uh,
and now it will cascade, right? So these labs will do things which will slowly move into things like quantum computers and things which eventually might become more readily available. Already people can log into simulators and
yeah.
things, but this is a process, but it has to start some at such a level. So I believe there's a quest driven science uh, typically leads to very big technological innovations, because you have something you desperately want to know scientifically, and you just push technology to its limits, and
Right.
then the spin-off keep coming out of it.
So it's almost like technology is trying to catch up with this goal that we have. That's even though if it's not
Yes,
particularly related
that's
to
very
technology,
important.
it will breed more. Okay.
Yeah, so once many people ask, why would theoretical and these live together? So someone poses a question, and that the community feels compelled to answer. Like there was an entire community which felt compelled to answer the question of whether gravitational waves could be detected. That led to the LIGO detectors. There would be similar quests. I mean, now, for example, I'm keenly pursuing this next generation CMB experiments, because that will look for gravitational waves. So it's related to gravitational waves from the kind of beginning of the universe,
Yeah.
right? Where beginning of what we call the standard cosmology, right? And we do expect these signals. And if you heard the Nobel Prize lectures of Kip Thorne and Ray Weiss, both mentioned this as the next scientific milestone.
Yes.
And this requires technology which is again has to make a break. So just like in gravitation waves, you needed to know how to measure atometers of displacement, 10 to the minus 18 meters
Yeah.
of displacement. Here you have to know how to measure atom watts of power. So
Okay.
it's basically like the receiver on your cell phone can measure about a tenth or a hundredth of a picowatt. Okay, that's very very sensitive. A lot of people worry about how much radiation is coming because we are the actual sensitivity of your cell phones is quite high, but we want to go 6 orders of magnitude
Yeah.
better, right?
Right. So moving into your research, you've contributed extensively to the domain of cosmology, especially the cosmological principle. Could you tell us more about what this principle is and also what your research focuses on?
Okay, so my research largely, uh, while I was a PhD student, the cosmic background explorer came up, and it was very clear within the decade, and by the time I became a faculty, that cosmological questions which are more of estimating the parameters of the universe, that was something that was going to be addressed and answered. But there was, and the whole community was driven towards that. I kind of saw that at some point you will turn around and ask how reliable are the assumptions on which cosmology is built.
Okay.
Okay, and not so many people were thinking about that observationally. Of course, people knew that these were assumptions. People had various things, but the fact that the same observations which are giving you detailed information about the universe given a particular model can be also turned around to question the assumptions of the model. So one such assumption is that the universe is the statistically on the average looks the same in every direction and
Isotropic.
isotropic, and it is also then homogeneous. right? If it is isotropic around everyone, it's homogeneous, and that's something that is just now we can probe it to a very high accuracy, right? So that's has been one of the strong research areas to delve deeper and deeper and get most accurate results. So starting from what we had from the WMAP satellite of NASA, and then going on to what Planck, and we are part of the Planck team to do this. Even now, recently we have, so this is one quest. Then similarly, there are other questions you can ask. There are certain things which we assume about the early universe, physics of the early universe. We don't know what happened, but we assume a simple model. The question is, do we need to rely so much on a assumed model, or can we actually use the data to question it? Okay, and that has been one of the research focus, largely my research focus has been to question the assumptions.
All right. So,
of a very successful theory. So I'm not out to necessarily find problems, but one should absolutely look for observational support for every assumption that you make.
I think that's the only data, at least in the field of astronomy and astrophysics. That's the only lab is your universe. So,
yes.
without the universe's data, it's all it will be difficult to talk about what theory actually is the right one. So we spoke a little bit about your research, but you've also spent much of your effort on your involvement with IUCA, which is the Inter-University Center for Astronomy and Astrophysics. It's a major stakeholder for the LIGO-India project. So could you talk a little bit about all of your years and all of the effort that you spent there, and also your involvement with bringing up LIGO-India as a collaboration?
Yeah. So when I came to IUCA, I came with a background of cosmic microwave background, and I worked for the first decade of my faculty life. That time the most promising or most up-to-date results on cosmic microwave background were WMAP, and I was working on that. But one of the things which used to always bother me was the data was from a satellite of NASA, right? And I did experience in my own career that there is something different about having the experiment, having an ownership of the experiment. I don't mean it has to be with you alone, or it can be collaborative, but there has to be a clear ownership of the instrument, and there has to be, again, as a theorist, I can't say I will have an instrument, but the Indian contribution to it should be
more self-reliant, basically.
More self-reliant. And so then when CMB had become very visibly very kind of famous, or the results were becoming something to be talked about everywhere, Indian scientists everywhere, very senior people started talking to me about, why aren't we doing CMB experimentation? And my answer was, I'm not an CMB experimentalist, so you should ask the experimenters why haven't they moved there. But nevertheless, from 2005, I did try to see if we could exploit one of our high altitude sites where, in the Himalayas, and set up some CMB experiment. And we were trying to do that, but then I also consulted the experimental community. The assessment was that the time it would take for us to get on with anything reasonable, the field would have moved on very far, right? And which was true. I mean, I talked to people who were part of the BICEP collaboration, which is has one of the most sensitive telescopes. And even in 2008, they were very confident that the 5 years that that I'll take in getting started, they would have moved to sensitivities which are not attainable, readily. So we will not really be competitive. And that sort of clarified in my mind one thing that I always felt was a problem in our scientific uh, pursuits in India, is not to catch on early enough. So, for example,
Okay.
if we wanted to do CMB, we should have at least started in mid 90s, some efforts. So I was at IUCA. IUCA always had a gravitational wave group, and I was aware of what's happening. Gravitational waves also, just like when 2000 Kobe detected the first microwave background anisotropy, the community which was involved abroad always expected it to make a detection, because that looked like very clearly something that could happen. I mean, you can never guarantee it, but so to me in 2007 8 looked very likely that within a decade gravitational wave detections will happen, given the advanced LIGO specifications
Hmm.
and the source. And the idea was to be ready for it. And the other thing I realized in India is we don't have a very strong collaborative culture. We don't have large collaborations. So we started off building the Indigo Consortium.
Yeah.
And being at IUCA, yeah, some support from IUCA, but the consortium was not tied to any institute. And that was very important. So it was an independent consortium of scientists, which we started building from 2009. And I think that was key in allowing us to have a reasonable community which could even hope to bid for LIGO India,
Right.
in 2011. So this was all kind of a bit of prior planning, and I really think that's very important. If as a community we want to really catch up, we need to identify early and make early investments into the field. I mean, in this case, of course, there were no huge investments, but the fact that you brought one, we could bring people together. And also, I think what helped was, there was a lot of support at the top. There has been. So I wouldn't say. So again, that's another thing I would like to say, that a lot of people do shy away saying that there's no support. There is, but you have to seek it. So
Right.
of course, so that's been my experience. Ayuka, of course, is something that I really very closely associate with. For years I've been there, and so there my research thing has been largely on cosmic micro background, but as from 2007 onwards, there's been this focus on trying to get the gravitational wave uh,
Back.
thing going.
Okay. So how are the gravitational wave backgrounds similar to the cosmic microwave background that you've studied?
It has a lot of similarities. We expect a stochastic background of gravitational waves. In fact, that was one of my first research works, was to show that Kobe signal could have also arisen from a gravitational wave background. And there's a particular ratio in which that happens, which nowadays is very well talked about as R, right? The ratio of primordial gravitational waves to perturbations. That was 1992. And so I had an interest in gravitational waves of cosmological origin. I also, in terms of LIGO, there was a period where I worked with one of my students on a method of mapping out the stochastic background of gravitational waves. And what was interesting about that is I think we brought in methods which were pretty routine in the cosmic microwave background field of
Okay.
deconvolution of the beam and things, which I think we readily. So, I mean, I would say the fact that if you now see maps which use the heel picks, that started with our papers,
Okay.
in the sense that the gravitational wave community, the introduction to these kind of packages happened because the student was working on it. And so that was just, and they are very similar in terms of what you can tell about it. So the stochastic gravitational waves, background does, one does expect it to kind of at some level of contrast reflect the large scale structure distribution, because sources would be where galaxies are.
Just similar to how cosmic microwave background radiation helped us look into the early universe, does gravitational wave background also help us say anything about the primordial universe?
Yeah, the gravitational waves from inflation would, the ones which you are looking for in the cosmic microwave background polarization, they'll be really the earliest moments of the universe.
Hmm.
The gravitational waves we are looking for at LIGO at this point, we are limited in range to be of very, very high cosmological significance, but that will change. I mean, we might start detecting the buzz, right? We are only detecting to finite sources now, right? I mean, specific sources, but then there's a noise background, which is expected to be, uncovered, and that would have some bearing on, what is happening in the universe. But that is not going to reach. Again, it's you're talking to a cosmologist. So for me, what is early
Okay.
is, for a common person, that is unimaginably early. So even the sources that we see in gravitational waves now are billions of years old, right? And they have traveled for billions of years, so they are early in that sense, a billion years earlier. But we are talking about looking absolutely at the beginning of the universe, which is 13 billion years ago in cosmology. So that will happen with primordial gravitational waves. Then LISA will start mapping out supermassive black hole coalescences. They and that has very strong implications for how structures formed in the universe. Okay, that again is earlier than the recent universe, but not the primordial universe. But still, that's a very important question. How did structures form? How did one of the big questions is, how did supermassive black holes form? Did they form by coalescence of smaller black holes or not? And Lisa may be able to answer such questions. They've been addressed many, many years back, as to what the promise of something like Lisa would be for these kind of. So it's going to be a completely new dimension of astronomy, astrophysics, which is opening up with gravitational waves. There's no question about it.
Right.
Okay, so as the sensitivity of the ground detectors, as well as things like LISA come on board, the pulsar timing array, and hopefully the polarization in the microwave background, these would be a completely new part of a completely new window, right? Different parts of a new window into the universe.
Right. So coming back to LIGO-India, could you say a few words about its evolution and the journey and where the project has reached today?
Yeah, so LIGO-India, I would like to first point out that one of the most heartening thing about the gravitational wave community has been the global cooperation. See, many areas, it is always there is some amount of competitiveness, right? So the highest most capable accelerators, particle accelerator in the US and Europe, why for similar signals? Gravitational waves, what struck me very early in the collaboration was something that was inherently global, in the sense that everyone needed all the observatories to work equally well to get far. I think that was something very heartening when we first started talking about a possible uh, experimental role that Indians could play. We didn't have a strong experimental community at that point. We hadn't identified as many people, and I remember going to an international meeting, talking to the top gravitational wave people, and I wasn't from the so much from the field. I had just worked on one of the problems there, but I was quite heartened to see the welcome we got and the encouragement to take it forward. And we were initially planning to be modest, which would have been probably a very viable thing of working as a part of the LIGO Australia. thing at some level, building up a community, and then later thinking of experimental things. But of course, there were many people who actually advised us the better way is to go for a detector, and that opportunity did arise. And when it came, I was really glad we could take it on. And it's been quite. I mean, there've been a lot of things to learn. I mean, what makes a big project click, right? And one thing very important to realize, and often scientists do not, because we live in our own kind of very elite ivory towers, is to realize that it requires everyone. LIGO-India wouldn't have been possible if, say, a district collector of a place who has nothing to do with science did not think or did not appreciate what you were trying to convey.
Right.
Or this level at which every single person, or someone who is whom we are counting on for giving the seismic results, or interpreting seismicity, or every part. So that was something that was very important in the early days, to identify the site. And that was something that is totally alien to me. I mean, no one trains for this kind of thing, but I put in a lot of effort to get the site,
Okay.
personally. And that was largely because I was, I used to talk to Govind Sarup a lot, who's built who probably has built one of the mega sciences in India, which is
Yeah.
Mati, and then
Yeah, Marty.
He, way back when we were just talking about this project in 2011, he said, you might think your biggest challenges are, the vacuum and all, but you have to get the site, right? And
Yeah.
in India, it's actually very tough to find that kind of thing. So that was, I think that was a really important journey that I had in Ayuka, leading from Ayuka with the site search, and then also getting the team together, trying to get other institutes together who would partner in the R&D activities, because there's no point in setting up a detector if there's no community which really talks to it or benefits from the technology, and
Yeah.
that is involved, or experimentally. So many groups have come up. So I think while I was there, so there were people from, and I'm really happy for the kind of support people gave, and stayed on from very early times till now. Believing that yes, something will happen. I mean, I give them a lot of credit, because for experimentalists, it's actually quite a bit of um, sacrifice, much more than a
Okay.
theorist, to say, okay, fine, I'll give some time to this, or I'll give some resources to this.
Okay.
Also, there have been very, very nice people who have lent us equipment for. I mean, so it's been a wholesome kind of experience. I wouldn't point to one thing, but it's been a project experience where I've seen, and also the interaction with the LIGO US people who have gone through something similar. So this is learning from their experiences and meeting some of them where so I think that was a very nice part of this.
Yeah, it's certainly really wholesome to even hear about this process of navigating such a mega science project here. It's kind of like a pioneering effort almost. Yeah,
And
sorry,
the
please go.
additional challenge in India, that's not something that is routine. In US, if you have a big project, there are mechanisms already in place to see how it will be done. Right? No, there will be particular structures put in, and in India, it's not that common, and it takes time to. There are projects other in other areas, but not in pure science, fundamental science, where there have been mega sciences kind of effort.
Right. So we're at the end of this conversation now. So I want to ask you, what is one piece of advice that you would like to leave the youthful listener with, who wants to
Okay.
who's aspiring to join the scientific community, who wants to work on things like gravitational waves, or even just science in general? What is one takeaway that you want to leave them with?
The thing I would tell people is they're absolutely rewarding quests that you can undertake in your scientific career, which is unparalleled because you have unfettered access to what you want to do. And so you should look at this journey more as an adventure, a scientific career more as an adventure than a job. It's one of the rare areas which allow you that.
Right. Powerful words. Thank you so much, Professor Tarun Souradeep, for
Thanks.
joining us. And yeah, everything you've said has been really, really rewarding to hear. And we hope to see, everything that LIGO India comes up with, and how it changes, how this mega science project changes the whole landscape for the scientific community here. So thank you again, sir.
Yes, I do hope that is one of the important messages. I think it will really change in a big way the ethics of how science is done. And not just like India, all the mega sciences have that potential.
Yeah.
Thank
Thank
you.
you, sir.